In this video, we will examine what we found, why it defies explanation, and what the latest data from 2025 and 2026 is revealing about visitors from beyond our solar system. Let's get started. For most of human history, we believed our solar system was isolated. The sun, our planets, the asteroid belt, the Kuiper belt objects, we thought everything here formed together 4.6 billion years ago and stayed here. Yes, we knew that space between stars contained gas and dust, but the idea that solid objects, rocks and ice, could travel from one star system to another seemed unlikely. The distances are simply too vast. Our nearest stellar neighbor, Proxima Centauri, is 4.2 light-years away. That's 25 trillion miles. Even traveling at speeds we can barely imagine, crossing that gulf would take millions of years. We assumed that while our solar system might occasionally eject small objects into interstellar space, we'd never actually see anything coming the other way. We were wrong. On October 19, 2017, astronomer Robert Warwick was analyzing data from the Pan-STARRS telescope in Hawaii when he noticed something unusual. An object was moving through our solar system on a trajectory that made no sense. When he calculated its orbit backwards, he realized this object hadn't originated from the sun. It had come from interstellar space, passed through our solar system at tremendous speed, and was already heading back out into the void. This was humanity's first confirmed detection of an interstellar object. The International Astronomical Union gave it the designation 1I/2017 U1, but it would become famous by its Hawaiian name, Oumuamua, meaning scout or messenger from afar. What happened next revealed a mystery that scientists are still grappling with today. At first, astronomers assumed Oumuamua was simply an asteroid or comet from another star system. But as observations accumulated, nothing about this object made sense. Initial data suggested it was extremely elongated, roughly 400 meters long, but only 40 meters wide, shaped like a cigar or pancake. No asteroid we'd ever observed had proportions like this. It was tumbling through space, rotating once every 7.3 hours, and its surface appeared surprisingly reflective, more like metal or dense ice than the dark, dusty surface typical of asteroids. But the real mystery came in June 2018. Marco Micheli, an astronomer working with the European Space Agency, was analyzing Oumuamua's trajectory when he noticed something impossible. The object was accelerating. Not much, just a tiny push, but enough to be measurable. It was moving away from the sun, slightly faster than gravity alone could explain. This is the moment everything changed. In physics, we have laws that govern how objects move through space. Newton's laws of motion and Einstein's general relativity tell us that an object's path is determined by gravity and momentum. If something accelerates without an obvious force acting on it, that's a problem. That breaks the rules. Now, there is one natural explanation for this kind of acceleration. Comets do it all the time. As a comet approaches the sun, ice on its surface heats up and vaporizes, creating jets of gas that push the comet like tiny rocket engines. This outgassing is easily visible. It creates the beautiful tails we associate with comets. So when Oumuamua started accelerating, scientists immediately looked for signs of outgassing. They found nothing. No gas jets, no debris cloud, no tail, no change in brightness that would indicate material being blown off the surface. The Spitze Space Telescope, one of the most sensitive infrared instruments we have, searched for any sign of cometary activity. Nothing. Oumuamua was accelerating without any visible means of propulsion. The scientific community fractured over this. Some researchers proposed that Oumuamua was coated in a layer of frozen hydrogen. Hydrogen ice is transparent and doesn't create visible outgassing, but it would still provide thrust as it evaporated. The problem with this theory is that hydrogen ice requires temperatures of around 3 Kelvin, just 3 degrees above absolute zero, to remain solid. Even in the cold of interstellar space, maintaining that temperature for millions of years seems unlikely. Other scientists suggested Oumuamua might be incredibly porous, like a loosely packed snowball. If it were porous enough, radiation pressure from sunlight hitting its large surface area could push it. But this would require the object to have a density far lower than any asteroid or comet we've ever measured. Then there was the shape problem. Those initial observations suggesting Oumuamua was extremely elongated were based on how its brightness changed as it rotated. The object brightened and dimmed dramatically, which typically indicates an elongated shape tumbling through space. But in 2019, Avi Loeb, chair of Harvard's astronomy department, pointed out something interesting. If Oumuamua were instead shaped like a thin disk or pancake, it would show the same brightness variations, but could also explain the acceleration through light sail effects. A flat, reflective object could be pushed by sunlight, like a solar sail. Loeb went further, suggesting that Oumuamua might be artificial, perhaps a light sail created by an extraterrestrial civilization. This created enormous controversy in the scientific community. Most scientists strongly rejected the artificial hypothesis, arguing that extraordinary claims require extraordinary evidence, and we simply don't have enough data about Oumuamua to conclude it's anything but a natural object with unusual properties. But the debate highlighted a fundamental problem. We don't have a fully satisfying natural explanation for Oumuamua's behavior. Every proposed theory has significant weaknesses. The object left our solar system in January 2018, and we'll never see it again. It's now more than 3 billion miles beyond Neptune, too far and too faint for any telescope to observe. We missed our chance to study it in detail, and that failure haunts planetary scientists to this day. But the story doesn't end there. On August 30, 2019, amateur astronomer Gennady Borisov discovered a second interstellar visitor using a telescope he built himself in Crimea. This object, designated 2I/Borisov, was completely different from Oumuamua. Where Oumuamua was mysterious and anomalous, Borisov behaved exactly like a normal comet. It had a visible tail of gas and dust. It was actively outgassing as it approached the sun. Spectroscopic analysis showed it contained water, carbon monoxide, and other compounds we expect in comets. The only unusual thing about Borisov was where it came from, another star system. Everything else about it was comfortingly familiar. This tells us something important. Interstellar objects exist, and they're probably common. Statistical models based on the detection of Oumuamua and Borisov suggest that at any given moment, there might be thousands of interstellar objects in our solar system, most too small or too distant to detect with current telescopes. The discovery of these two objects has fundamentally changed our understanding of the galaxy. Space between stars isn't empty, it's filled with wanderers, rocks and ice that have been ejected from their home systems and now drift through the cosmic void for millions or billions of years. But while Borisov answered some questions, it made the Oumuamua mystery deeper. If Borisov represents a typical interstellar comet, then what was Oumuamua? Why was it so different? In the years since these discoveries, scientists have proposed increasingly exotic explanations. In 2020, Yun Zhang and Douglas Lin suggested Oumuamua might be a fragment of a planet that was tidally disrupted, torn apart by gravitational forces, creating an unusually elongated chunk of planetary material. In 2021, Stephen Desch and Alan Jackson proposed it was a nitrogen iceberg, a fragment from a Pluto-like world in another star system. Nitrogen iceberg is reflective like Oumuamua's surface and sublimates without creating visible tails. Each theory explains some of Oumuamua's properties, but struggles with others. The nitrogen iceberg theory explains the acceleration and lack of visible outgassing, but requires the object to have come from a very specific type of planetary system. The planetary fragment theory explains the unusual shape and composition, but doesn't fully account for the acceleration pattern. We're left with a puzzle, and puzzles like this are how science advances. When something doesn't fit our models, it's telling us our understanding is incomplete. Now let me tell you what's happening right now, in 2025 and 2026, because the interstellar visitor story is far from over. Astronomers are preparing for the next phase of discovery. The Vera Rubin Observatory in Chile is scheduled to begin full operations soon. This telescope will scan the entire visible sky every few nights, automatically detecting anything that moves or changes. Scientists predict it will discover dozens, possibly hundreds, of interstellar objects over the next decade. Each new discovery will help us understand whether Oumuamua was a bizarre anomaly or represents a common class of interstellar object we simply hadn't seen before. There's also a growing push to be ready when the next interesting visitor arrives. NASA and ESA have been studying the concept of an interstellar object interceptor mission. The idea is simple. Design a spacecraft that can launch on very short notice when an interesting interstellar object is detected, accelerate to tremendous speeds using gravity assists from planets, and actually catch up to the visitor before it leaves our solar system. Such a mission could answer the questions about Oumuamua that we missed our chance to investigate. What is it really made of? What is its actual shape? Does it have any organic compounds or unusual isotope ratios that would tell us about its home system? The technical challenges are enormous. Interstellar objects move fast, typically 15 to 30 kilometers per second relative to the Sun. Catching one would require speeds we've rarely achieved with spacecraft. New Horizons, which flew past Pluto, reached about 14 kilometers per second. To intercept an interstellar visitor, we'd need to go faster, possibly using solar sails, electric propulsion, or even nuclear thermal rockets. But the scientific payoff would be transformative. By studying an object from another star system up close, we'd learn about planet formation conditions around other stars, about the composition of the interstellar medium, about how objects age during millions of years in the space between stars. Meanwhile, Voyager 1 continues its journey through interstellar space, providing us with direct measurements of the environment these objects travel through. Voyager crossed into interstellar space in 2012, and it's been sending back data ever since. What it's found is surprising. The density of the interstellar medium is higher than expected, about 0.1 particles per cubic centimeter. That might sound like nothing, and it is incredibly thin by Earth standards, but it's enough to have significant effects over cosmic timescales. An object traveling through this medium for 1,000,000 years would experience erosion from constant bombardment by these particles. This might explain some of Oumuamua's unusual properties. Voyager has also measured cosmic ray intensity in interstellar space. These high-energy particles are 3 to 4 times more intense outside our solar system than inside it. The Sun's magnetic field provides some shielding, but in interstellar space, there's no protection. Over millions of years, this radiation would alter the surface chemistry of any object, potentially creating unusual compounds or changing the reflectivity of the surface. Could this explain Oumuamua's shiny appearance? We don't know yet, but Voyager's measurements are giving us the data we need to find out. There's also the question of what interstellar objects tell us about the frequency of planetary systems in our galaxy. Every star we've studied with sufficient precision shows evidence of planets. The Kepler Space Telescope discovered thousands of exoplanets, and statistical analysis suggests nearly every star has at least one planet. If planets are that common, then planetary formation processes, which naturally eject some material into interstellar space, must be creating a vast population of wanderers. Oumuamua and Borisov are just the first ones we've noticed. They're the tip of an enormous iceberg. Think about what this means. Right now, as I speak, there are probably hundreds of objects from other star systems passing through our solar system. Most are too small to see, but they're there. Some might be ice-rich comets, like Borisov. Some might be rocky asteroids. Some might be objects so exotic we don't have names for them yet. Each one carries information about another star system, another planetary environment, another corner of our galaxy. They're like messages in bottles, drifting across the cosmic ocean, and we're finally learning how to read them. But there's a deeper mystery here, one that touches on fundamental physics. In 2020, quantum physicist Leonard Susskind and others proposed something called the holographic principle. This idea suggests that all the information in a three-dimensional region of space can be encoded on the two-dimensional boundary of that region like a hologram. This principle has profound implications for black holes and the nature of reality itself. Some physicists have begun to wonder if information, in some quantum sense, can be preserved even as objects are destroyed or transformed. Could the information encoded in the atoms of interstellar objects, information about where they formed and what they experienced, survive their long journeys through space? This isn't mystical thinking, it's serious physics. Quantum information theory tells us that information cannot be destroyed, only transformed. When an object breaks apart or vaporizes, the information about its original state doesn't disappear. It becomes encoded in the particles and radiation that result. Over cosmic timescales, as interstellar objects are bombarded by radiation and gradually eroded, the information about their origins becomes spread across space in incredibly complex ways. In principle, with perfect knowledge of all the particles and fields in a region of space, you could reconstruct the history of every object that passed through. In practice, this is impossible with current technology, but the theoretical possibility is fascinating. Some researchers have taken this even further. In 2023, Roger Penrose proposed an updated version of his theory about quantum consciousness. He suggests that quantum processes in the brain create information states that, according to the laws of quantum mechanics, cannot simply vanish when we die. Where does this information go? In principle, it disperses into the universe, becoming part of the quantum field that underlies all of reality. Now, I want to be very clear here. This is highly speculative physics, at the very edge of current understanding. There's no evidence that consciousness survives death in any meaningful sense, and most physicists are extremely skeptical of these ideas. But the theoretical question is interesting. If information cannot be destroyed, and if consciousness involves quantum information states, then what happens to that information is a legitimate physics question. This brings us back to interstellar objects in an unexpected way. If objects can carry information across the galaxy, encoding in their atoms and molecules the history of where they've been and what they've experienced, then in a sense, or they're messengers, carrying data across cosmic distances and timescales, an object ejected from a planetary system 1 billion years ago carries information about what that system was like 1 billion years ago. When it passes through our solar system, we have the opportunity to read that information, to learn about places and times impossibly distant. The problem is, we're not very good at reading the message yet. When Oumuamua passed through, we barely managed to observe it before it left. We got enough data to know it was strange, but not enough to understand why. It's like receiving a letter written in a language we don't fully comprehend. We can see the words, but the meaning eludes us. Borisov gave us more data because it stuck around longer and behaved more predictably, but even there we're still analyzing what we found. Still trying to extract every bit of information from the observations we made. This is where the next generation of telescopes and missions becomes crucial. The James Webb Space Telescope, launched in 2021, has infrared sensitivity that far exceeds anything we've had before. If another interstellar visitor appears, Webb could potentially detect organic molecules, unusual isotope ratios, even the faint heat signature of the object itself. These observations could tell us about the composition of the object's home system, about whether it formed in the warm inner regions near a star or the cold outer reaches. The extremely large telescope, currently under construction in Chile, will have unprecedented light-gathering power. It could potentially detect interstellar objects much smaller and fainter than what we can see today. And then there's the question of artificial objects. I mentioned Avi Loeb's controversial suggestion that Oumuamua might be artificial. While most scientists remain skeptical, the possibility has prompted serious thinking about how we would recognize an artificial interstellar object if we saw one. What would a probe from another civilization look like after millions of years traveling through interstellar space? Would it still be functional? Would it be recognizable as technology? These aren't idle questions. The Breakthrough Listen initiative, funded by Yuri Milner, is actively searching for evidence of extraterrestrial technology. When interstellar objects pass through our system, Breakthrough Listen points radio telescopes at them, searching for any signal that might indicate artificial origin. So far, every object checked has been silent. But the search continues. Here's what we know with certainty as of January 2026. First, interstellar objects are real and probably common. Second, they can have properties we don't fully understand, as Oumuamua demonstrated. Third, each new discovery teaches us something about the galaxy we live in. Fourth, we're getting better at detecting these visitors, and we'll find many more in the coming years. Fifth, the next decade will likely bring the first detailed, up-close study of an interstellar object when an interceptor mission succeeds. And sixth, every single one of these discoveries challenges our understanding and pushes the boundaries of what we know about planetary systems, stellar evolution, and the nature of the space between stars. But there's one more thing, something that became apparent only recently. In late 2025, astronomers analyzing the trajectory data from both Oumuamua and Borisov noticed something interesting. When you calculate backwards where these objects came from, taking into account their speeds and directions, you can estimate which stars they might have originated from. Oumuamua appears to have come from the direction of Vega, one of the brightest stars in our night sky, about 25 light-years away. But when you trace its path back millions of years, accounting for how stars move through the galaxy, Oumuamua didn't actually come from Vega. It came from somewhere else, somewhere we can't pinpoint because too much time has passed and too many gravitational interactions have altered its course. Borisov's origin is similarly uncertain. It came from the direction of the constellation Cassiopeia, but where exactly, we don't know. This uncertainty tells us something profound. These objects are ancient wanderers, ejected from their home systems millions or even billions of years ago. They've traveled so far and for so long that their origins are lost to time. They're cosmic refugees, orphans of stellar systems that might no longer exist, carrying within them the only remaining evidence of worlds we'll never see. And this brings me to the final, most profound mystery. If our galaxy is filled with these wanderers, objects ejected from planetary systems across billions of years, then space between stars is not empty void, it's an archive, it's a record of galactic history, written in rock and ice, scattered across light years. Every interstellar object is a page from that archive, a fragment of information about the past. The challenge facing humanity now is learning to read that archive, to extract from these silent visitors the stories they carry. In 2025, the European Space Agency announced preliminary approval for a mission called Comet Interceptor. This spacecraft will be positioned at a stable point in space, waiting. When an interesting interstellar object is detected, it will launch, accelerate toward the visitor, and deploy 3 smaller probes that will study it from multiple angles. This mission could launch as early as 2029. If successful, it would give us our first detailed look at an interstellar object, our first real chance to read the message these cosmic wanderers carry. Meanwhile, work continues on even more ambitious concepts. The Breakthrough Starshot initiative aims to send tiny spacecraft to Alpha Centauri using powerful lasers to accelerate light sails to 20% the speed of light. If successful, these probes could reach our nearest stellar neighbor in about 20 years. They would become humanity's own interstellar wanderers, carrying our message outward, just as Voyager carries the golden record. Perhaps billions of years from now, long after our sun has died, these tiny probes will pass through some distant solar system, and perhaps inhabitants of that system will detect them, study them, and wonder about the civilization that sent them. This is the universe we're discovering. Not empty and cold, but filled with travelers. Not isolated islands of matter around stars, but a galaxy connected by wanderers, by objects carrying information and history across impossible distances. We are only now beginning to understand this. We are only now learning to read the messages written in the trajectories and compositions of these visitors. And here's what keeps me awake at night. If space is filled with wanderers, if every planetary system ejects objects into interstellar space, then somewhere out there are pieces of Earth, objects from our solar system, ejected by gravitational interactions with Jupiter or Neptune, now traveling through the galaxy. In 1,000,000 years, some of them will pass through other stellar systems. Will anyone be there to see them? Will they recognize these fragments of our world for what they are? Will they wonder about us the way we wonder about Oumuamua? The clock is ticking. Right now, somewhere in the darkness between stars, the next visitor is approaching. It might arrive next month or next year. It might be another icy comet like Borisov, or it might be something as strange and inexplicable as Oumuamua. When it comes, we'll be watching, we'll be ready. And with each new discovery, we'll understand a little more about the galaxy we inhabit and our place within it. The Vera Rubin Observatory will begin its survey soon. The Comet Interceptor mission is moving forward. The James Webb Space Telescope is operational and waiting. And somewhere, in observatories around the world, astronomers are watching the sky, waiting for the alert that will tell them another messenger has arrived from the depths of space. When that happens, everything we've learned from Oumuamua and Borisov will be put to use. We won't miss our chance again. This is the frontier of astrophysics in 2026. Not looking outward at distant galaxies, though that remains important, but looking at what's passing through our own cosmic neighborhood, learning to read the messages written in rock and ice, decoding the archive of galactic history, one visitor at a time. We are archaeologists of the cosmos, and these interstellar objects are our artifacts, our primary sources, our direct connection to worlds we cannot reach but can, in a small way, begin to understand. The universe is speaking, we're learning to listen, and what we're hearing is more strange, more wonderful, and more profound than we ever imagined.